So today we have Duncan O'Dell from McMaster University, and he will tell us about Schwinger pair production considered as a non-Hermitian problem. So go ahead, Duncan.
Okay, thank you very much, Andres and Francisco, for this opportunity to address everyone. This work was somewhat accelerated. I was expecting to be talking in May, but the schedule was rearranged. So I must admit, it's still a little bit of a work in progress, but I think the main ideas are there. So hopefully I can present a somewhat coherent talk.
Thank you for switching, Duncan. Thank you for swapping your slot.
No worries. So I'm kind of a little bit new to this group, so I have a lot to learn still about non-Hermitian problems and so on. So I put my email on this slide. If you wish to communicate with me, please do so. If I've missed papers of yours, I'm very sorry. So you can always contact me by this email and let me know what I've missed. Okay, please let me change the slide. There we go. I thought I would just say a little bit. If you don't know where McMaster is, it's in Hamilton. Okay, the beautiful city of Hamilton, which is Lake Ontario. Okay, so this is Canada up here. This is the US border. Is this line going through the middle of Lake Ontario? There's New York State. So Hamilton's here. It's about an hour's drive outside of Toronto. So there's Toronto, there's Hamilton, and the Niagara Falls are very close. And we got lots of waterfalls around, not just the Niagara Falls, it's the city of waterfalls. So if anyone is ever in the area, please drop by and I'd love to speak to you. Okay. For some reason, this is not letting me change. Okay, there we go. So this work actually that I'm going to talk about was mainly done by my PhD student, Schwinger. And it builds on work of a previous PhD student, Ryan, here. And it's certain parts of it, as may become evident, are in collaboration with a particle physicist, colleague of mine, Cliff Burgess. And so parts of what I'm going to say have already been published actually in this paper, which was all about the problem of fall to the center and trying to describe that using something called point particle effective field theory. So let me explain the motivation for this work a little bit, so give it some context. So I am absolutely nuts, okay, about singularities. And in particular, so wave singularities. They display various different scales. Okay, so what you can see is maybe on the left-hand side here, something that you've maybe seen on a bright sunny day. You get this caustic structure in your coffee cup. Okay, so there's the light gets reflected. The light is sort of coming from the top of the screen, like is shown in the picture at the bottom, gets reflected off the back side of this cup and forms this sort of bright, hopefully you can see it, this sort of bright cusp shape on the surface of the coffee. And this structure isn't just random. It turns out that in 2 dimensions, and so the surface of the coffee is like a 2-dimensional screen, it turns out that the structurally stable singularity in 2 dimensions is in fact cusp point, which is the joining point of 2 fold lines. Okay, so I'm using the language there of catastrophe theory. So if this cup was a plastic cup and you could press in the back wall a little bit, you would distort and shift this cusp, but it would still have some integrity. It would remain a cusp shape. And if we were dealing with optics, this cusp shape is actually a singularity of the ray theory of optics. Okay, so you can see that it's the envelope of these rays, and it turns out that along this cusp, the intensity diverges according to the sort of geometric optical theory. But of course, the reason singularities are so interesting is because they're a place where one theory fails and we need to introduce another theory. So we can do better than the ray theory, of course. So we can introduce the wave theory. And it turns out that this cusp shape is dressed by an interference pattern, which is universal. So in 2 dimensions, these cusps are the sort of classical singularities, and then they're dressed by this wave interference pattern, which you can see is the amplitude and here's the phase of it. So you get these kind of, you can think of them as vortex, anti-vortex pairs, these phase singularities appearing inside the cusp. And these were understood by Pearcey, an American mathematician, back in 1946. And you can read all about the different, these wave catastrophes that dress all of these ray singularities in the last chapter, chapter 36 of the NIST Handbook of Mathematical Functions, the thing that Abramovitz and Stegun became, was updated a few years ago. Okay, so the cusp is the structurally stable singularity in 2D, but then as you go up in higher dimensions, you get these more and more complicated structures. In 1D, it's just a point on a line, but in 2D it's a cusp, and then in 3 dimensions we get these things, and then in 4 dimensions and so on, you get more and more complicated singularities. And so all of these are dressed by their own sort of universal wave patterns, local to the singularity. But what I'm really interested in is the next step in that sort of program. And I was very much inspired by this paper by Ulf Leonhardt, which is where you have singularities of the wave theory, and you need to do something to the wave theory to remove that singularity. So an example of this is a wave passing over an event horizon. So you can see here that the wavelength gets smaller and smaller as this wave propagates towards this event horizon. In fact, the wave number depends on the 1 over basically the distance from the event horizon, as the inverse of that. Okay, the inverse of r minus the position of the event horizon with some coefficient. And if we just put that into a sort of ordinary wave expression, you see that because when you do this integral, you're going to get a log. Okay, so you get a logarithmic phase singularity at an event horizon. And so your wave theory breaks down. So we first remove the ray singularities by introducing waves, and now the wave theory breaks down. So what do we do? Well, the answer to that is to go to a second quantized theory. So you don't no longer treat these waves as classical, but you introduce, well, in this case, it would be something analogous to Hawking pairs that are produced, and that will remove the singularity, is the idea. So that was the inspiration for this work. Okay, but now I'm going to shift into a sort of slightly more specific example, and that's the Schwinger effect. Okay, so the Schwinger effect is where if you have the vacuum, and now imagine there's 2 metal plates, and you now put a voltage on these plates, so there's an electric field, a constant electric field between the 2 plates, then you can actually, the vacuum is unstable and will produce particle-antiparticle pairs, positron-electron pairs from the vacuum. And Schwinger, I mean, he wasn't the first person to think about this. Heisenberg and all sorts of other people thought about it, but Schwinger calculated the pair production rate. Okay, and so somehow, you know, we're invoking here, you know, the particle nature of quantum field theory. So in this expression, and what in the rest of this talk, this sort of curly E will be the electric field strength, Q is the electric charge. And so we can sort of understand this at a basic level by, or at least the characteristic length scales. If you think of the Compton wavelength, then is giving a characteristic length scale. Then the work done by the electric field over the Compton wavelength is given by this expression, right? So this is the force times the distance, force QE times the distance. And then a characteristic scale is when that work is equal to, let's say, the energy to create a particle or antiparticle, 2mc squared. And that's exactly this dimensionless quantity that appears in the exponent here. Now, typically, the electric fields that are required are huge. And so this hasn't actually been seen, at least in this simple format. People are trying to do dynamical versions of dynamical fields, it's very powerful lasers and so on, but it's in its original form, it has never been seen. It's not going to stop us thinking about it, though. Okay, so so the plan for how this talk is going to go is we're going to describe this particle-antiparticle production, at least. Okay, so I'm going to treat it on a classical level, despite what I said about antiparticle pairs. We'll still see at the classical level that we can calculate the production of particle-antiparticle pairs. So we'll start from the Klein-Gordon equation, and we're going to map it to the inverted harmonic oscillator, okay, which is a sort of paradigm of an unstable system. And from there, we're going to map it to, oops, I see my plan has got slightly messed up here. Sorry, this was supposed to be two separate points. We're going to map the inverted harmonic oscillator to a Q dot P Hamiltonian. And then we will, in fact, not use the Q dot P. We'll map that to a Q dot P squared Hamiltonian. And finally, we will map that to a Schrodinger equation with an inverse square potential. So sorry, there's a whole bunch of steps in this calculation. And at this point, we'll invoke a sort of particle physics phenomenology, an approach to dealing with the. You may know that the Schrodinger equation with inverse square potential has issues with it. You get these it's a non-self-adjoint problem, but we'll solve that in a particular way using something called point particle effective field theory. And finally, I'll get back to the Schwinger effect. Okay, so here's the Klein-Gordon equation, okay, describing a charged field, but a scalar field, and where it's going to be, we're going to on this field, we're going to have an electric. Sorry, on the matter field, we're also going to impose this electric field, which we introduce through this gauge term here. Okay, so this is just the Klein-Gordon equation, but now with this electric field term in here. And one thing to note at this point is that it obeys CPT symmetry, so charge conjugation, parity, and time reversal. Okay, and so the way we're going to convert this, so this is a relativistic theory. We're going to convert it into an ordinary quantum mechanics problem by this ansatz here. Okay, so we're going to choose a particular mode with frequency omega, and we're going to do separation of variables in this form such that we convert this equation into this one down here. And now with a little bit of redefinition, you can see that this is in fact the equation for it's a Schrodinger style equation for the inverted harmonic oscillator. Okay, so by redefining this sort of somewhat complicated piece here as this new coordinate, so don't get confused. So this curly E here is the electric field, whereas this sort of straight E here will be our eigenvalue in this equation. And for later convenience, I'm pulling out a minus sign. So E here is a positive quantity, and it just depends on the mass and the charge and the magnitude of the electric field. So as the electric field gets very strong, you can see that this eigenvalue gets very small. So here I've plotted so this is basically, this is the momentum squared minus some coordinate squared. That's this inverted harmonic oscillator. And these particular, for any particular eigenvalue, we sit at some particular negative energy. And in fact, this will never be above the barrier, will always be below the barrier. It'll always be a tunneling problem. You can see that as the electric field gets very large downstairs here, we'll eventually tend towards where the barrier is as small as it can be. We're just sitting at the very top of the barrier. We've already lost some symmetry at this. I mean, it's now this time-independent equation. We've got anyway. This one obeys CP symmetry. All right. So what we will eventually want to introduce into this is the idea that that we have particles and antiparticles in this problem. And so the idea is imagine we send in some particles, let's say with positive charge, we'll call those particles. Then particles with negative charge are the antiparticles. And so what you can have is this reflection and transmission process of this barrier. So if you send in these particles from the right here traveling left, they may reflect as positive particles. If they tunnel through and keep going on the left-hand side, they're antiparticles, because to get pulled over in this direction and to fall down this side of the potential, they have to have a negative charge to be pulled to the left, to my left, at least as I'm looking at the screen. Zoom can reverse. Interesting parity problem with Zoom. That you get, to fall down this side, you must be an antiparticle. In other words, you must have a negative charge. Whereas to get pulled back, to get reflected and pulled back in this direction, you're still a particle. So this is a problem you can think of in this inverted harmonic oscillator version of the problem. It's a sort of, I'll call it fall to infinity, because these particles will like to fall either side of this potential. We're going to contrast that. We're going to map this problem to a fall to the center as we keep mapping the Schrodinger equation onto the Schrodinger equation with the inverse square potential. But we're not there yet. We're still with this inverted harmonic oscillator. So when we plot the phase space, so this is momentum and this is position and these new variables, you can imagine particles coming in from the right, and they either reflect off the barrier or they tunnel through to the other side, and then they would continue on some trajectory down here. So the way I've also introduced, apart from these pi and psi coordinates, I've introduced linear combinations of them, Q and P. Okay, and so the way this is arranged, this diagonal line here separates Q less than 0 from Q greater than 0. So it turns out that everything with Q greater than 0 will be a particle, and things with Q less than 0 will be an antiparticle. Okay, so this problem, in principle, we could solve it now using parabolic cylinder functions. Okay, but it's not an ordinary, the complication is it's not an ordinary quantum mechanics problem, because particle number won't be conserved. Okay, charge will be conserved, but particle number won't be conserved. So in going from the Klein-Gordon equation to the Schrodinger equation, we've got to bear that in mind. We're not going to get things like transmission plus reflection must equal 1. Transmission probability plus reflection probability must equal to 1, because we have the potential for this particle production. And that makes our treatment of this in terms of parabolic cylinder functions, these W's or these Whittaker functions, a little bit delicate. But what we would like to find are these alphas and betas, these that describe the amplitudes of these two independent solutions. But this particle production is going to cause us, some issues. So what I'm going to do, instead of trying to solve the problem in terms of parabolic cylinder functions, I'm going to try and map it to something else. So using these coordinates, then it turns out that this inverted harmonic oscillator maps to a Q dot P Hamiltonian, which is shown here. Okay. Now things look a bit simpler here. For instance, if you solve Hamilton's equations for this Hamiltonian, then you get this exponential decay or growth of the coordinates. And so we can plot things now in this Q dot P phase space. You can see that there's an incoming, this would be the incoming particles coming in from the right. There's the reflected ones then appear and come down here, and there's the transmitted ones over here. And also the quantum mechanics problem at first sight seems simple. If we work in the Q representation, then we can convert this eigenequation for this Hamiltonian with eigenvalue E into, in the Q representation, it takes this form. Okay, and that has a very simple solution in terms of this sort of this monomial solution here with some amplitude A. And now you can see finally what the connection was to this to these quantum catastrophes I was talking about at the beginning. That this you can re-express this thing here. It has some exponent nu in this form, and so you can see that you have a logarithmic phase singularity as a function of the coordinate. So this wave oscillates faster and faster until at the origin it's oscillating infinitely fast, and the whole concept of a wave breaks down. We need a better theory at that point. However, you know, although this seems like a simple solution, it's clearly a bit pathological because we do exactly have this singularity at the origin.
Can I ask a quick question, Duncan?
Yeah.
What happened to the PT symmetry? I think zeta went to I zeta under PT, no? So these P's and Q's, PT is completely lost, right? Or
so this still has CP symmetry. So if you send Q to minus Q, we don't in fact change this equation because psi will go to I psi.
yes, that's what I understood. So in your capital P and Q, you pick up an I now, no? So
yes, that's correct.
on the next page.
Yes.
Yeah, yes, here the P's and Q's.
Yes, but then this I, so then you multiply these two together, and your I's will become a -1. But then also this E will become, this E was defined, remember it had a Q somewhere in it here. So this E would also change sign.
But the P's and Q's, capital ones, they don't have a well-defined symmetry now, right? Yeah, just
as a function of what? As you change X? As you change Q, you mean?
well, your original symmetry. I mean, you pick up an I in front of the zeta, and I mean that. How does Q transform under the original PT? It doesn't go into minus Q, for instance, or anything well defined.
Right. Q, I think, is going to go into IQ, right?
Well, there's a pi there.
Pi will also pi is, sorry, going the wrong way. Pi.
That's the one. This is not okay. Okay, that's what I missed. Okay, yeah. Okay. Thank you.
Okay, so right, but okay, so there are some math. Although the problem looks a bit simpler. I mean, the solutions, we don't have to deal with parabolic cylinder functions. There are some issues with this. As may well be well known to many of you, this Hamiltonian, this Q dot P, is self-adjoint on the half real line, but not the full real line. And the space, this Q space, is really broken up into sort of two disjoint pieces. There's the Q less than 0 is the antiparticles. The Q greater than 0 is describing the particles. And our solutions to this little sort of first order equation here need to be broken up. So it's described in this paper by Berry and Keating here, and other places too. Needs to be broken up into two pieces, separated by these capital thetas of the Heaviside step functions. So we still have these two coefficients describing somehow amplitudes of particles and antiparticles, but in between at the origin where q equals 0, everything blows up. And trying how to connect A and B, as we would normally do in a Schrodinger sort of problem of tunneling through a barrier, that really is not, that kind of approach doesn't work here. These are really two separate spaces, and we can't really match the wave functions on the boundary, that they're diverging and so on. So this is still a sort of pathological problem. So the trick we're going to use here, so credit to Sriram for working this out, is that rather than the Hamiltonian q dot p, we're going to use its square. Okay, and in that way we will make the problem, we'll be able to use the whole real line. And at least, well, let's say we can map it onto a more familiar problem, which is the Schrodinger equation with an inverse square potential. So that, of course, we're going to double the number of solutions. So at the end, we'll need to double the potential number of solutions. So we're going to need to be judicious about selecting out just the ones we want. But you can sort of see, in some sense, we include both signs of this eigenvalue. So we're sort of including both particles and antiparticles on equal footing, and including them both in the same equation. And this equation will exist across the whole real line. Okay, so if you again write this equation in a in the Q representation, then it takes this form here. Okay, so and we can rewrite it a little bit into this canonical sort of form of the, you can think of it as a Schrodinger equation with an inverse square potential by changing phi into some new function chi. Okay, so this looks like the Schrodinger equation, but with a 0 eigenvalue on the right-hand side. So the zero energy case. Okay, so this kind of problem is a bit of a classic. So when we have the Schrodinger equation with inverse square potential, in particular, it has this property where you have scale invariance. So if we scale x, just writing it, general Schrodinger equation here, and you change x to lambda times x, because the kinetic energy term and the potential energy terms scale in the same way, there's no intrinsic length scale in the system. So you just pull out a lambda squared and absorb it into time. So this has classical scale invariance, in the sense, by classical here, I mean it's a sort of classical wave theory. There's no second quantization going on at this stage. Just treat this as a classical field equation.
Frida has a question in the chat. Frida, you want to ask the question?
Yes, if you go, I think 2 or what transparencies back, there was your wave function in Q, or 3, I don't know, there was a plot where you show this. Yes, exactly this. My first feeling would be that the larger Q, the more oscillatory your solution should be. Why is it exactly in the inverse way? The closer you come to Q equals 0, the more oscillatory you get.
Okay, well, I guess the answer to that is that we have this this 1 over square root of Q here. So the idea is basically we can rewrite this Q to this with this exponent in terms of a log. So you get it's exactly this logarithmic singularity. So as Q gets very small, it's going to oscillate very, very fast.
Okay.
I don't have a magic explanation other than that. I mean, that is an honest plot of what it looks like, the real and imaginary part. Okay.
But you understand that far outside at an inverted oscillator, the energy increases and somehow the wave function should get more oscillatory, no?
Yes, but we've mapped the problem at this stage to, okay, so we've pulled out, we've mapped the problem onto this Q dot P1, basically. So this is the origin of Q space.
Yeah, well, the only place where I know that things get oscillatory if you go to the Stokes cone of oscillators, where you, or the anti-Stokes cone, where you have this change from exponential increase to exponential decay. They get oscillatory behavior, which is very strong. Well,
okay. I mean, I guess what I'd say is what we've effectively done is map the problem from fall to infinity, which was the inverted harmonic oscillator, where I agree with you in that picture, you know, the waves will, their wavelength will get shorter and shorter as you move away from the origin, to one which is now really fall to the center. So we've, in some sense, inverted, I mean, in fact, now you ask your question, perhaps I should have mentioned that. In some sense, we've sort of inverted space, or taken the logarithm of it, because now the singular place will be at the origin.
There's another question from Mamashi. You want to ask it? Mamashi, you want to ask the question? You have to unmute yourself. We can't hear you. You're mute. Maybe we leave it to the end.
Okay.
No. Okay.
Okay. I have a question about the eigenvalue of an inverted oscillator. Why you use minus E? Yes. No, not this. Before this. Before. No.
Want me to keep going?
This. Okay, this. The Schrödinger equation for particle in inverted harmonic oscillator. Why you have minus E, the eigenvalue with a sign, with a negative sign?
That's a choice. So that this quantity here, I mean, it comes ultimately from this negative sign here. Okay, so when we do this this separation of variables, we'll pick up this negative sign here. Well, yeah, in going from here to here, we pick up this negative sign, and rather than including, you're right, I could have included the minus sign in the definition here. It's just a choice I made at this stage. So that E is positive, but it's true. You're right. It's a negative eigenvalue in the sense that we're below the barrier. It's just a choice I made.
Okay.
Okay.
Okay. Thank you.
Okay. Okay. Where were we? So okay. So the point was, this is where I was trying to get. We've mapped this problem onto a Schrödinger equation with an inverse square potential. And this has this classical scale invariance, and indeed you get fall to the center, okay, which goes back to Frieda's point that the problem is now not at infinity or plus or minus infinity; it's at the origin. And so this is known in classical mechanics. If you have some potential, some potential that's at least goes as 1 upon r squared or is more singular even, but we're right at this case of 1 upon r squared. You can overcome your angular momentum barrier. And so if you're in 3 dimensions, I mean, we're not in 3 dimensions, but it's a problem that's well known, then you can get fall to the center classically. And you also get it in quantum mechanics. This is the radial equation now for this 1 upon r squared potential, depending on your angular momentum, and you have a 1 upon r squared potential, an attractive 1 upon r squared potential. Then you can get, if you go above a certain critical value of your coupling G here, then you get this the fall to the center. So your energies become unbounded from below. You can have any negative energy you like. Bound states become continuous, and it's basically a non-self-adjoint problem. So it's pathological, and one has to cure it in a particular way by imposing boundary conditions which fix this. And that's what I'm going to discuss in the time that remains to me. So this is a well-studied problem. Here are a list of sort of papers. However, if you've worked on this and I'm not citing your paper, then please send me an email and I'll take a look. Okay, I wanted to say a little bit about, because the sort of community I come from is quantum gases. And so this problem is one that's got some interest from the quantum gas community over the last few years. So for example, you can realize these similar scale invariant problems if you have a Bose-Einstein condensate, for example, in a pancake trap, so an incredibly tight trap. So the system is essentially 2-dimensional. So you have your kinetic energy term for each particle, and it turns out that then the interactions at these very low temperatures can be described by delta functions, and we're in 2 dimensions, so it's this 2-dimensional delta function. Then the 2-dimensional delta function will also scale as 1 over a length squared. And so again, you can pull out this 1 upon length squared factor when you try and scale it. So it has no intrinsic length scale. In fact, though, you also need, typically these gases are held in harmonic traps, and that does break the scale invariance in 2 dimensions. But it turns out it was shown by Pidievsky and Roche some time ago that there is in fact still a hidden symmetry in this problem, an SO2-1 symmetry. Another example is given by the Efimov effect, which was predicted by Efimov in the early 1970s, I think, in nuclear physics. It's where you can have 3-body bound states, even where you don't have a 2-body bound state. Anyway, this is a sort of artist's rendition of it's not to be taken too seriously, but it's an artist's rendition of what these trimers look like, these 3-body things. And it turns out that if you look in this hyperspherical coordinate, and you're at very low energy, so you don't worry about anything else, low energy limit with these ultra cold gases, then your effective equation describing the problem in these hyperspherical coordinates can be reduced again to a Schrodinger style equation with a 1 upon r squared potential. So people are investigating these experimentally. The key thing is that this symmetry here gives you, you can come up with a generator of excitations, and it turns out you get a ladder, so that the motion that this gas can do is this kind of breathing motion, and it turns out that the energies of you get a ladder, sort of like a harmonic oscillator of sort of equally spaced states, which depend exactly on this on the trap. They don't depend in any way on the interactions between the particles. It's a really remarkable sort of exact solution of this many-body problem, purely in terms of these of the energies of the trap, as though the interactions kind of go away. And however, that's all in the classical theory. This ladder of states. If you second quantize the problem, you get something called a quantum anomaly, where this scaling symmetry of the classical theory is broken. And in these gas experiments, what that turns out to be is that you get a very slight shift of these, so they can measure these breathing frequencies, and you get a very slight shift away from away from twice the trapping frequency. And that is really an effect of the fact that these gases are made of individual particles. They're not this smooth sort of field. So again, it's this effect of second quantization. Okay, so that was a sort of commercial break, I suppose, for those experiments. So if we get back to the one upon this one upon q squared problem, okay, so we have this Schrodinger equation, and look now. So we're interested, for example. So you notice that the solutions to this equation, when you look at very small q, can be written in this form. Okay, these in terms of these monomials where s plus and s minus depend on this eigenvalue, well, what was an eigenvalue in the original problem in the inverted harmonic oscillator, but now it appears as part of the depth of the potential in this inverse square problem. And so there's two regimes according to this phenomenology of these Schrodinger equations with 1 upon q squared potential. So there's a subcritical regime where e squared is less than 0, and a supercritical where e squared is greater than 0. And in the subcritical regime, s plus and s minus are different from each other, and that means that these two solutions at least behave differently at the origin. They diverge in slightly different ways, and it allows you to choose these, to do something, to choose. I mean, ultimately you want to find out what these two coefficients, c plus and c minus, are. And when there's two solutions behave differently, you stand a chance of doing that. But in the supercritical regime, both of these solutions diverge in the same way, and there's really nothing to choose between them. If I was solving, the Coulomb problem, the hydrogen atom 1 upon r, I'd have a solution one that grows to infinity and one that doesn't, one that's bound, and I would know which solution to choose for a physical problem. But here they both diverge in the same way. So we need some way, we need to cure this problem that you can think of sort of the problem is incomplete. We need to introduce some extra physics, some boundary condition that lets us choose between these two solutions, or at least what combination of them we need. So you can think of this as a sort of very low energy theory that works at large q, and we've got to introduce some cutoff or something at a very small q that allows us to choose our solutions. And so these are called extensions, and people usually are interested in self-adjoint extensions of this problem. How to impose boundary conditions to make this a self-adjoint problem. So so I'm going to attack this problem in a somewhat different way than the way you may have seen before, using something called point particle effective field theory. So this is a way we can introduce either self-adjoint, or importantly for this problem, it's going to be a non-self-adjoint extension, because we're going to want to describe this particle production. And so the idea is that we introduce something towards the origin of our problem that introduces some sort of microscopic physics, and that will impose a boundary condition. It's basically going to be a delta function that we're going to put at the origin. And we're going to, so there's the sort of length scale in which the 1 upon q squared problem lives, the low energy length scale. We have the very high energy sort of microscopic physics that we still need to insert into our problem. And then there's some boundary between them where we're going to regulate our theory. We're going to match the two theories at this boundary. Okay, and so the way to do this in a systematic way, as I said, is this point particle effective field theory, and you can do it through the action. So this is the action of the Schrodinger equation, actually, for this 1 upon q squared potential. But now we're going to add to it some new physics, which is going to be our boundary condition at the source. Okay, and we're basically, what the idea is, we treat the source. So it's a bit like a multipole expansion. You know, if you have a charge at the origin, or you have a, let's say you have a group of charges at the origin, then you can do a multipole expansion such that, you know, at large distances only the monopole is important, and the dipole is a smaller correction, and the quadrupole is still smaller correction. So we can describe whatever object we wish to put at the origin, which is going to impose a boundary condition on our system, through some systematic expansion here. So I must say, you know, in this problem, it's a bit of a hammer to crack a nut. We're just going to stick with the simplest situation here, where we couple the density, the modulus squared of our sort of low energy theory, our 1/q squared theory, to some source term at the origin described by this delta function, and lambda is going to be our coupling constant between this low energy 1/q squared physics and some boundary condition sort of specified by the source. So for example, one way to realize, so it's described in our previously published paper, but the problem we were interested in there is if you have dipoles, so polarizable particles, okay, so they're neutral, but they can be polarized in an electric field, and you have let's say you have a wire that's coming out of the screen towards you, then this wire, if it's charged, creates a field that will polarize the particles. And so it creates a 1/r potential, but then because of the polarization of the particles, it turns out that these dipoles will feel a 1/r squared potential, exactly one of these 1/r squared potentials. But what's generating this, you know, what one shouldn't forget in this problem is in fact the wire, and that's generating boundary conditions at very small scales, and can be used to regulate the problem. So you match the two problems at this boundary epsilon. Okay, so if we extremize this action, so the total action is this 1/q squared, and however we're regulating the problem with this particle, take the sum of the two, and we extremize the action. What basically this does, this is just a fancy way of saying we're going to add a delta function at the origin, but we want to know what the size, the coefficient of the delta function is. Okay, so whatever the size of this coupling lambda is, will be exactly the boundary condition that will tune our allow us to tune these solutions to match well, eventually the Schwinger problem. Okay, so all we've done is we've replaced a 1/q squared problem by adding this extra delta function at the origin. And what lambda is, so if you integrate over this equation, okay, just integrate it over a little range around the origin, you can relate this coupling lambda to the logarithmic derivative, usual thing when you're matching wave functions in scattering theory, to the logarithmic derivative at the regulator, at this regulator. So we don't go inside this, sorry, we integrate just over this scale between plus or minus epsilon. And we'll match these two theories on this boundary. Okay, so so the point is that that adding this delta function breaks this scale invariance. Okay, it basically, what it does is it fixes the ratio between our two solutions, the coefficients of our two solutions. As I said, that there's many ways to do this, you know, not using this point particle effective field theory, but this just simply gives us sort of a more algorithmic way to do it. And we'll just choose the simplest possible coupling. You know, I could have added extra, I could add derivatives and higher powers and so on, but this is the simplest. And so whether you have absorption or emission, so at the origin, is determined by whether lambda is real or whether it's complex. So if you work out the probability current for this problem, for this Schrodinger equation, including this delta function correction, what you find is that you can get net flow into the origin if your coupling constant is complex. Okay, so we're going to want to choose our, in the particular Schwinger problem that we're ultimately interested in, we're going to choose this coupling such that it matches our Schwinger, the fact that we're producing particles, that we have this non-conservation of particles. So we could, describe it to be a sink or a source at the origin, just by letting this lambda be complex. And so this is already, in most of the papers I've seen, people are usually interested in these self-adjoint extensions, but here we're really interested in this non-unitary case. And in particular, if one looks at the continuity equation for this problem, rather than having 0 on the right-hand side, you get this source term, which is just the imaginary part. So basically, it's going to depend on whether lambda here is imaginary or not. And then we can choose it to be a source or a sink. Okay, now, however, there's more issues with this. So we're going to match these two solutions on the boundary here, this intermediate scale epsilon. But the problem is this coupling constant lambda is going to run depending on the scale we choose for epsilon. Okay, so this running is going to break the scale invariance of the problem unless we have fixed points in our renormalization group flow. But what we want is that our physically observable things like transmission and reflection coefficients will depend on our two amplitudes of our wave functions at sort of large distances, or in other words, basically the ratio of C plus and C minus. So what we want, this is you have to trust me that this, you can, using this theory, you can show that the ratio of these two coefficients obeys this little formula here, okay, where zeta here is this was the eigenvalue, remember, in our inverted harmonic oscillator equation. It depends on this way, and what we want is that this ratio of these two coefficients that we find from our theory in this way, from this Schrodinger equation, including the 1 upon q squared potential and the delta function, well, their ratio, which is a physical thing, shouldn't depend on epsilon. So we can do, in other words, when we take the derivative with respect to epsilon, this, which is the size of this intermediate scale, nothing that is physically observable should change. So, so it turns out then that one can derive this little flow equation for the coupling constant lambda. Okay, and one can pose this in a sort of renormalization group way. See, I'm running a little short of time. So let me explain that very quickly. So it turns out that if you calculate the flow of this coupling constant lambda, okay, so to make things simple, sorry, I've redefined things a little bit. So capital lambda in these axis labels is related to little lambda, the original coupling constant in this way. Sigma is minus I times this eigenvalue. And it turns out that the renormalization group flow, you get these limit cycles. You get these two fixed points, which are on the imaginary axis. The imaginary axis runs up here. And these correspond, so these are, only these 2 points here are scale invariant, and they correspond to a pure sink and a pure source below. Okay, so if you calculate, if you, for instance, follow the red line, oops, should be going around this way, follow it round and round, then what you find is that this coupling constant has this logarithmic, log periodic behavior as a function of epsilon, the boundary at which you choose things, at which you match your solutions. Okay, so finally we want to bring this back towards the Schwinger problem. So we have, so let me generalize the problem. So we have this 1 upon q squared Schrodinger equation. I'm going to add in the fact that this in our problem, this should be 0 k squared, but we're going to introduce finite value of k, but it's okay because when q is small, we will be able to ignore this. It'll become irrelevant eventually. But this allows us to map this problem onto the Hankel equation, and this has well-known solutions. So so the solutions to this equation. So we have when q is greater, when we're outside of this boundary, when we're on the right-hand side of our problem, we have the incoming wave and the reflected wave can be expressed in terms of the second Hankel function and the first Hankel function. So R is a reflection coefficient here. So these we want to find, and for the transmitted case, we have this transmitted amplitude here. We basically want to find what R and T are. And so these are determined exactly by matching the solutions at Q equals plus or minus E. Okay, so this don't worry about the details on this rather technical slide, but when you look at small q, okay, very close, then you can exactly pick out, remember these monomial solutions with these logarithmic singularities, you can see them appearing here. So this is just to say that effectively what we've done is, by this process, is we've been able to, in the same sort of solution, have both particle and antiparticles appearing and put them on equal footing, ultimately, because we squared the Hamiltonian. Okay, but we want to find this relationship between R and T. Okay, and we do that by matching our solutions right at this boundary. And what one finds is that you get this relationship between the reflection and transmission coefficients. Notice that this is not of the form, well, if you were to take, it's not of the form of sort of R plus T equals 1. We get this non-Hermitian contribution. And so ultimately our coupling constant is given, when we match at these boundaries plus or minus A, this scale that we choose, we can extract our coupling constant. So there's a particular, so we can label, there's a subcritical for the case and a supercritical case, but we're always in the supercritical case when we have the Schwinger problem. And we can label each of these trajectories where they cross the imaginary axis here. Okay, and we'll call these, these are E star, these points E star, which we cross the imaginary axis. Okay, as I'm running out of time, I'll just kind of skip to the result that that in this way you find this relationship between the transmission amplitude and the reflection amplitude, and it depends in this way. You can see that it's not of the form that you'd expect of a unitary problem, but you can relate the transmission and reflection coefficients to these objects one finds from these actual points that label the trajectory. So from this renormalization group flow, you can pick out the right values of lambda, but they don't depend on the way that you regulated the problem. They don't depend on the value of epsilon, this scale, this non-physical sort of scale that we introduced. Okay, this is my last slide, Andreas, if you're getting worried. So at the end of the story, the probability of producing a pair, so you can extract it from this equation, that the degree to which this is non-unitary is given by this expression here, which, when I take you back to our sort of first or second slide, also remember this eigenvalue depended on the inverse of this electric field strength here, epsilon. And in this way, one reproduces the Schwinger's result. So in Schwinger's result, one needs to sum up or ultimately integrate in a sort of discretized version. All these, remember, we did this separation of variables in particular modes. One needs to include all the contributions from all the different modes and sum up all of these terms. But one finds in this way, one gets back Schwinger's result. So this is the probability to remain in the vacuum. Of course, then the probability to produce pairs is 1 minus this, such that the total probability sums to 1. Okay. What have I told you? So we can treat the Schwinger effect as a non-Hermitian quantum mechanical problem in terms of this. Ultimately, we map things onto the inverse square Schrodinger equation. And there's this formalism I told you about, this point particle effective field theory, where you can treat, you can do this in a self-adjoint or non-self-adjoint way. You can introduce, depending on this coupling constant, you can put in physics sort of at the origin, as it were, that's absorbative or emissive as you choose. So what remains to do is this connection to quantum catastrophes, which I hinted at the beginning. Okay, that's it.
Thank you very much, Duncan. So if we all unmute ourselves and give Duncan a round of applause. Thank you. Any questions?
Yes. I was wondering if you can treat in the previous transparency, this, can you hear me?
I think so, yes.
Okay. In the previous transparency of this, I think you can treat the previous one, I guess. The previous one. I think you can treat the non-unitarity by assuming that there is some kind of
this one or the next one?
No, that's okay. That's okay. Just by assuming that you have absorption, so not only reflection and transmission, but you have an absorption coefficient, and then you can recover unitarity.
Yes, but I guess the point is here, we don't want unitarity, because we want to describe this particle production.
Yeah, yes, this is true.
Yeah, so, and that, I guess, is the point, that most people are looking to solve these self-adjoint extensions, but we're really interested in generalizing this to the case where you don't necessarily have that, where you have absorption or you have production of particles. And so here, yes, we're producing particles due to the Schwinger effect. I guess, you know, what I maybe should have emphasized more is, and I guess what I would like to extract from this group, this audience, is the degree to which people are treating, you know, that you know about this being done before, that people treat these non-Hermitian problems, you know, they treat, let's say, particle production in field theories through this non-Hermitian sort of quantum mechanics.
Yeah.
I don't know if anyone has seen that before or has any comments on it. You know, in some sense, it's not, you know, we started off with a perfectly legitimate Klein-Gordon equation, which, you know, we weren't putting sinks and sources into that. That's a perfectly, you know, sort of well-defined Hermitian problem.
Right.
And whereas the sort of non-Hermitian problems I've seen so far, you know, people are putting in absorption and emission, you know, they have, you know, pump, you know, if you're talking about in optics or something, or you put in a source or emission. Whereas here, I'm just wondering if it's really a legitimate use of this non-Hermitian sort of idea. You see what I mean?
Yes.
That's a question to everyone, actually.
I mean, that's a question I had at the beginning, is sort of related. I mean, how
And you
how
still
does
have.
PT symmetry flow through your talk? What role does it play? It was
I
kind
think
of mentioned at the beginning, but then you don't really make use of it, right?
No, that's kind of because this is a work in progress. So
Okay.
I think, so what I think is, let me go back here. It's basically, let me just move the speaker view over here. I think it's broken where you have this. So for the Schwinger effect, it's always broken basically, because you always get, even for small electric fields, you're always getting a weak amount of particle production. So if we go back to the final slide, here, this pair production, no matter, I mean, in fact, there's no sort of threshold. It's just very weak. If you have a rather small electric field, then we'll only get a small pair particle production, but it'll appear. It'll just be small, and then as the electric field gets larger and larger, it eventually becomes, the probability will tend to 1, that for sure we're producing pairs of particles. But where it comes in, I think, is exactly this, the fact that we have complex values of our coupling constant. In other words, when we have this fall to the center problem, we go back still further. As soon as we have fall to the center, I think it's you break time reversal symmetry, I think. And that's manifested by getting this complex coefficient, this complex boundary condition, by having this delta function with a complex coupling.
Duncan, I think if you come from this Klein-Gordon equation where you have somehow positive and negative energy states, you go to this Schrödinger equation with the inverted oscillator, and then you choose your scattering from the right side. Somehow you break a symmetry which in the end by your PQ squared trick reinfer so that you get a certain kind of PT symmetry. So my question would be here, what does this mean in the inverse for the inverse harmonic oscillator? So you have now your Schwinger pair production problem, which you obtained from the inverse harmonic oscillator, and you got some boundary conditions for the wave function somehow of the Schwinger problem. What would be now, if you return to the inverse Schrödinger equation, this mean for the boundary condition of the inverse harmonic oscillator? That's my question.
So I think what your question is, what are the values of alpha and beta here? Right?
Well, you have claimed now some boundary conditions
Yes.
for the Schwinger problem, and you determined certain conditions for your interaction, for your coupling. Now, how do these values of the coupling and the boundary relations relate back to the inverse oscillator? I always, when I treat this inverse oscillator, I am puzzled how to choose the boundary conditions because I know that at a far infinite distance, the wave functions get very oscillatory. But I could say, okay, I want to have standing waves, or I want to have tunneling without reflection, or whatever.
Yeah, so I don't have here the expression for these coefficients alpha and beta in terms of the other coefficients C plus and C minus, but there's something that can be worked out. I don't have an expression for them, but basically they're going to be related to each other via this exponential exponential to the minus e, where e is exactly this eigenvalue, because that's going to be describing the pair production. In other words, this tunneling probability through here is exactly governing the pair production rate. But I'm afraid I don't have the translation back into this version of the problem. So we've gone through like 3 different problems mapping one to the other, and I don't have the expressions for alpha and beta, but it can be worked out.
And my feeling is by using your PQ square trick, when you make the inverse direction, you get suddenly two oscillator problems. One maybe either you scatter from the right, the other from the left. I don't know. You have not a unique inverse oscillator, which that's my feeling, but I'm not sure.
Yes, it's true. One needs to select out just a set of the possible solutions. If you don't, basically what you do, what you find when you square this solution is you get, rather than the Schwinger pair, you get two options for the Schwinger pair production. One is that it had this sort of exponential decay, and the other is as a function of the inverse field strength, and the other is where you get an exponential growth. And so you can throw that out. That is something you are able to throw out on physical grounds. Yeah.
So if you know the boundary conditions for the oscillator, tell me, yes.
Yeah, okay. Well, okay. I mean, maybe if Sriram, my student, is on the call, he may. Are you there, Sriram? I can't see everyone.
Yeah, so,
Yes.
probably if I can comment. So the thing is, we can go back to the inverted harmonic oscillator eigenstates, the parabolic cylinder functions, from the inverse square states through what is called a quantum canonical transformation. So using the generating function that relates the canonical transformation from the pi psi variables to capital QP variables can be used as a kernel to map wave function in the capital Q space onto the psi space. So that would relate the coefficients in the inverse square problem to these alphas and betas.
Yeah, so I don't have these expressions here, I'm afraid, but
yeah,
they exist.
Well, I worked more than 2 years on the inverted oscillator, so I'm very curious what comes out here. It's really interesting.
Okay, well, we certainly can send you that once we have it written up.
Any more questions? I have one very general one, slightly unfair, but just out of interest. Are we any closer to measuring pair production experimentally? Do you have any idea on this, or have you heard any rumors?
I don't know about the sort of, you mean the conventional, where they're with this laser source. I don't know the status on that. I mean, in the dynamic there's various, dynamical Casimir effects that has been seen using sort of electronic mapping onto very fast electronics. Basically, you have cavities, the dynamical Casimir effect, you can produce particles by moving one boundary very rapidly, and you can map this onto a sort of LC circuit, and there they can move these boundaries extremely fast. And so there they can see analogs of pair production. But in the straightforward Schwinger, like electric field, try and pull out particle-antiparticle pairs, I haven't heard that there are any where they're at with that.
Thank you. Yeah, it's a field strength problem. No, I mean, we are not that high in field strength. Yeah.
Yeah, I guess I'm into the analogs more, the low energy analogs, and there it's very easy. You can produce, for instance, your Bose condensate. If you have a Bose condensate, it behaves like the vacuum, and then you can excite particles out of it very easily. You're not really producing particles; they're already there. They were just in a particular sort of sleeping state, if you like. So the analogs are all easy, and the mathematics is the same, but you may not get satisfaction.
You're still cheating, no?
Yeah, it's cheating.
Any more questions?
They have noted a lot of positron production in the vicinity of black holes. So maybe there is some origin for that.
Oh. Wow.
Let's thank Duncan again. Thank you very much, Duncan.
Okay, thank you.